right now, you are looking at a screen.
Most likely, yeah.
And the text rendering on that screen, the operating system running the device in your hand, and, the security protocols keeping your bank tab safe while you listen to this, they all share the exact same architectural DNA.
It's actually wild when you think about it.
It is, and almost all of it was built by a guy who, well, he basically just wanted to play a bootleg video game about space travel.
Yeah, a video game. That's the origin story.
So, welcome to you, the learner, to this deep dive. Today, our source material is a single Wikipedia article.
Just one.
Yep. And our mission is to explore how one single, intensely curious person quietly laid the foundation for the entire modern digital world we rely on every day. His name is Ken Thompson.
And, it's fascinating to think about because we interact with this logic constantly. I mean, all the time.
Oh, absolutely.
Every time you run a search or spin up a cloud server or even just type a special character on a keyboard, you are navigating this invisible metropolis that Thompson basically designed from scratch.
Okay, let's unpack this, because to really understand how we got this invisible metropolis, we kind of have to look at how Thompson's brain operated from the very beginning.
Right, the early years.
Yeah. Born in New Orleans in 1943. And he wasn't just casually interested in machines, As a kid in grade school, and keep in mind this is long before commercial computers were accessible to anyone outside, like a massive university or government lab, he was solving arithmetic problems in binary.
In grade school.
In grade school.
That isn't just a quirky biographical detail, right? It's basically the skeleton key to his whole career.
How so?
Well, he wasn't just learning binary as, like, a trivia fact. He was actively training his brain to internalize the stripped-down fundamental logic that governs machine architecture.
Oh, I see.
Yeah, he was conceptualizing things at the absolute hardware level before he even had the hardware to play with.
Which perfectly brings us to the late 1960s. So he's at Belle Labs, which was essentially the most prestigious corporate research facility on the planet at the time.
Oh, yeah. Legendary place.
And he's working on Multics. Now, Multics was this massive, ambitious, incredibly bloated mainframe operating system.
Very heavy.
Right. While he's there, he creates a programming language called Bon. And more importantly, he builds a game called Space Travel.
Ah, yes. The game.
Yeah. It was this pretty sophisticated simulation of the solar system where you basically navigate a ship around different planets.
Which, for the 1960s, was really pushing the limits of what a computer could do in a recreational sense.
Totally. But then Bell Labs pulls the plug.
Right. They just bail out.
Yeah, they realize Multics is getting way too heavy, too complex, and they withdraw from the whole project.
But Thompson doesn't really care about the corporate strategy, does he?
No, not at all. He just wants to keep playing space travel.
That's the best part.
So he scavenges around and finds this discarded, totally obsolete PDP-7 computer. But he realizes he can't just port the game over. The environment doesn't exist.
He basically has no foundation to run it on.
Exactly. He actually has to build an entirely new operating system just to host his little game.
What's fascinating here is how this shifted the whole paradigm, right?
Huh.
Because some of the most critical infrastructure in computing history wasn't born from a grand corporate mandate.
Right.
It was born from a programmer's playful desire to just keep a game running. And because he was working on this clunky machine with very limited memory, he couldn't build a massive monolithic system like Multics.
He had to be efficient.
Exactly. He was forced into extreme elegance. So he, along with Dennis Ritchie and Rudd Cannaday, starts building tools that are highly modular.
Right, like the hierarchical file system.
Yes.
Instead of the old method where files were sort of dumped into flat structures or, tied directly to specific physical hardware locations, they created the concept of a root directory branching out into subdirectories.
Precisely. The whole tree structure we use today. And they also developed the command line interpreter, device files, and crucially, the concept of pipes.
Okay, I want to pause on pipes because to me, this completely changed how I understand software.
It's a huge deal.
Right. Because before pipes, if you had a program that sorted data and another program that printed data, they couldn't just talk to each other.
No, they were completely isolated.
One program had to do its job, write a physical file to the disk, and then the next program had to wake up and read that file from the disk. It was so clunky.
It was incredibly inefficient. I mean, agonizingly slow.
So Thompson invents the pipe, which It just routes the standard output of one program directly into the standard input of another.
Seamlessly.
Yeah, it's like moving from a world where every single building requires its own custom-built power plant to a world where Thomson basically invented the standardized electrical grid.
That is a great way to put it.
The pipes just let you plug any specialized appliance into any outlet, and the current flows instantly.
And that shifted the entire philosophy of software engineering. The whole Unix philosophy became write small programs that do exactly one thing well and let them work together.
Do one thing perfectly.
Right. Brian Kernighan actually ended up suggesting the name Unix as a pun on the bloated Multics, specifically to emphasize that Unix did one thing at a time elegantly.
I love that. But, once you build this beautiful new standardized grid with Unix, you face a brand new problem.
You need better tools to actually build things on.
Exactly. You need to write the software that runs on it,
Yeah.
and assembly language is just too slow and way too tied to specific hardware. Which leads us directly into his work on programming languages.
Right, because if you want Unix to run on different types of computers, you need a systems programming language that is, well, high level enough for humans to read and write quickly, but it also has to be low level enough to interact directly with the memory and the hardware.
So Thomson literally just creates one.
As you do.
Yeah, he creates the B programming language because Unix needed a system language.
Yeah.
And B is the direct, immediate precursor to Dennis Ritchie's legendary C language.
And C is arguably the most vital programming language in history.
Oh, no question.
It gave Unix its vocabulary, Unix provided the environment, and C provided the incredibly fast portable language to build within that environment. And Thomson always maintained that C grew up alongside the continuous rewrites of Unix. They were completely symbiotic.
Okay, so Thomson helps pave the way for C, which obviously goes on to dominate the world. But let's fast forward to the 2000s.
Okay, skipping ahead.
Thomson is at Google. He teams up with Rob Pike and Robert Griesmer to co-develop a completely new language called Go.
Oh, yes. Go.
And the source material is explicitly clear about the catalyst for this. They designed Go because they absolutely despised C++ boot.
He really did. It's kind of a legendary hatred in computer science circles.
Thomson famously called C++ a garbage heap of ideas that are mutually exclusive.
Ouch.
Yeah. But wait, let me push back on this. If the C language is his baby and is the gold standard for foundational computing, how does he absolutely roast C++R, which was designed as its direct object-oriented evolution? I mean, is this just an old-school coder being stubborn about new paradigms?
I wouldn't call it stubbornness, actually. It's an absolute fundamental intolerance for bloat.
Ah, back to the efficiency thing.
Exactly. It reveals a continuous thread in his career. See, C++ tried to be everything to everyone. It added object-oriented programming, templates, exceptions, just incredibly complex feature sets layered on top of each other.
It got heavy.
Extremely heavy. To Thomson, who cut his teeth stripping an OS down to fit on a discarded PDP-7, this was architectural heresy. It slowed down compilation times and made code bases totally unreadable.
So when they built Go, they wanted to violently swing the pendulum back to simplicity.
Yes. When Thomson, Pike, and Griesmer sat down to design Go, they mandated this really strict consensus rule.
What was the rule?
All three of them had to explicitly agree on every single feature before it could be added to the language. Yeah. If even one of them objected or felt it added unnecessary complexity, the feature was thrown out. No extraneous garbage. They wanted a language that compiled instantly and handled modern concurrency, like running multiple processes on multi-core processors cleanly.
And if you are wondering if that obsession with simplicity paid off, Go is the language currently powering Docker, Kubernetes, and massive chunks of the modern cloud infrastructure you are probably using to stream this very audio.
It's everywhere now.
But his pursuit of elegant logic wasn't just about the back-end infrastructure. Here's where it gets really interesting.
Okay.
His obsession with efficiency forced him to revolutionize how computers handle basic human text, and even human games.
Right. If we connect this to the bigger picture, once you build an operating system that runs lean, you have to solve the problem of how humans actually search and manipulate data inside it without bogging the machine down.
Right. You need a way to find things fast.
Exactly. So in the 1960s, Thomson develops the QED editor and later the standard Unix editor, AID. And inside these, he implements regular expressions.
Now, Anyone who has ever written a script knows about rejects.
It's a lifesaver.
It's basically a sequence of characters that specifies a search pattern. Instead of finding the exact word file, you can write a pattern that says, find me every string that starts with F, has 2 wildcards, and ends in E.
Right. But it's important to note, Thompson didn't invent the mathematical concept of regular expressions.
They didn't?
No, the math existed. What he did was figure out how to make a computer execute them at blinding speeds. He invented an algorithm, which is now known as Thompson's construction, which takes that abstract human search pattern and systematically converts it into a non-deterministic finite automaton.
Okay, hold on. That sounds like a sci-fi weapon. Break that down for me.
Fair enough. Basically, he built the compiler for search queries.
Oh, I see.
Instead of the computer painfully checking every single letter of a document against the search pattern one by one, Thompson's algorithm translates the search pattern directly into optimized machine code on the fly. Yeah, it turns a text search into a high-speed state machine. It is the exact reason why you can search a massive log file instantly today. Almost every modern program that uses regular expressions owes its speed to his notation.
That's incredible. And, his impact on text goes even deeper. If you're reading an article online right now or looking at a menu on your smartphone, there is a 90% chance you are relying on another one of his inventions.
Universal translator.
Yes. In 1992, he and Rob Pike developed UTF-8.
Which solved a massive, massive crisis in the early days of global networking.
Because encoding was a total nightmare back then, right?
A complete nightmare.
Yeah.
The computer only knows ones and zeros. It needs a map to translate those bits into human letters. And the old standard, ASCII, was great for English.
Right.
But terrible for the rest of the world. Different regions created different encodings for different alphabets. And when those computers tried to talk to each other across the early internet, you'd just get screens full of broken, unreadable gibberish.
So how did UTF-8 actually fix it? Because why didn't they just make every character take up more memory to fit every single language in the world into one giant map?
Well, because that would have broken every existing system that was already running on ASCII. And it would have bloated file sizes immensely.
Back to the bloat problem.
Always back to avoiding bloat.
Yep.
The genius of UTF-8 is that it is a variable width encoding. Thompson and Pike designed it so that a standard English letter still only takes up one single byte, exactly like the old ASCII standard. So it is 100% backward compatible.
Ah, so the older systems didn't even realize they were reading a new format.
Precisely. They just read the English text like normal. But if you type a complex Japanese kanji or an Arabic character, UTF-8 dynamically expands to use 2, 3, or 4 bytes to render it.
That is so clever.
They use the first few bits of the byte as a signaling mechanism to tell the computer, hey, exactly this many bytes belong to the current character. It was so elegant, so foolproof, that by 2019, UTF-8 was the encoding for over 90% of the World Wide Web.
It really is the universal translator of the digital age. And that logic, that ability to map complex possibilities into perfect, executable rules, it applies to play as well.
Oh, the chess stuff.
Yes. Remember, this whole journey started with a video game. Well, in 1971, Thompson wrote a chess-playing program for the first version of Unix. Later, he teamed up with Joseph Condon to build Belle.
The chess machine.
Yeah, a hardware-assisted chess machine that actually won the World Computer Chess Championship.
And again, if we connect this to the bigger picture, whether he is dynamically allocating bytes for a Chinese character or evaluating positions on a chessboard, he is fundamentally solving for universal rules, universal truth.
Yeah.
He actually wrote programs that generated the complete enumeration of chess endings for all 4, 5, and 6-piece endings.
Okay, wait, so complete enumeration. That means he didn't just teach the computer a heuristic strategy, right?
Wait, no heuristics.
He effectively built a mathematical map of every single possible move left on the board so that the computer literally couldn't lose.
Exactly. It's called retrograde analysis. He built what are called endgame table bases. You work backward from every possible checkmate position, mapping every single path.
Mind-blowing.
By pre-calculating all of this, once a game of chess is reduced down to 6 pieces or fewer, the computer completely stops thinking or calculating probabilities. It just consults Thompson's map.
It just knows.
It knows with absolute mathematical certainty the perfect sequence of moves to force a win or force a draw. It is flawless logic.
The man is just relentless. I mean, in 2004, he even helped implement Alan Turing's unbuilt 1948 chess program, TuroChamp.
Oh, that's such a great story.
Turing devised the logic for a chess AI before a computer even existed that was powerful enough to run it. And half a century later, Ken Thompson steps in to actually bring Turing's theoretical code to life.
It's almost poetic, really. He is the guy who turns theoretical logic into functional reality. He establishes the ground rules that we all trust.
Which perfectly brings us to the most chilling part of our deep dive. We've just spent this entire time exploring how Thompson built the foundations of trust, right? The file systems, the languages, the text encodings. We inherently trust these systems with our corporate secrets, our medical records, our power grids.
We have to.
But what happens when the chief architect himself taps the microphone and proves mathematically that the building you're standing in is fundamentally compromised?
This is, without a doubt, one of the most legendary moments in the history of computer security. So in 1983, Ken Thompson and Dennis Ritchie win the Turing Award.
Which is huge.
It is the pinnacle of computer science.
Yeah.
It's basically the Nobel Prize of the field.
And Thompson gets up to deliver his acceptance speech, which he titled Reflections on Trusting Trust. And instead of a standard victory lap, thanking his colleagues and reflecting on his legacy, he delivers this terrifying paper outlining a persistent compiler backdoor attack.
The famous Thompson hack.
Yeah.
It completely dismantled the fundamental illusion of security in software.
Okay, but let me push back on how terrifying this really is. Because if the source code for an operating system is open, like Linux or, early Unix, wouldn't another programmer eventually audit the code, see the malicious instructions, and just delete them?
You would think so.
Right. So how does a backdoor stay hidden if everyone can read the code?
Because the malicious code isn't in the human-readable source code. That's the absolute brilliance of the hack.
Wait.
To understand it, you have to look at the compiler. The compiler is a program that translates the human-readable C code into the binary machine code that the computer actually executes.
Okay.
Thompson explained that you could write a backdoor into the compiler itself.
Oh, I see where this is going.
He designed a compiler that was trained to recognize when it was compiling the Unix login program. Whenever it saw that specific login code, the compiler would secretly inject a backdoor password into the resulting binary, allowing anyone who knew the password to log into the system.
Unbelievable.
And the original programmer looking at their clean source code would see absolutely nothing wrong.
Because their code is clean?
Yes.
It's the translator that's actively lying to the machine during the conversion process.
Exactly. The translator's lying. But here is the truly terrifying part. The part that really answers your question about someone spotting it eventually.
Okay, lay it on me.
A compiler is just a piece of software, right?
Right.
Which means that it has to be compiled by an older compiler.
Uh-huh.
Thompson showed that he could train his corrupted compiler to recognize when it was compiling future versions of itself.
Oh, wow. Oh, no.
Yes. When it recognized the compiler's source code, it would inject the backdoor inserting logic into the new compiler's binary.
So it covers its own tracks perfectly.
Completely perfect.
Let me get this straight. You inject the malicious code once. Then you compile the compiler. Then you literally delete the malicious code from the human-readable source.
Yep.
So anyone who audits the source code from that day forward sees a perfectly clean, totally secure compiler. But because the executable binary of the compiler is already infected, it just keeps passing the invisible corruption down to the next generation forever.
Yes. It is a self-replicating invisible ghost in the machine. You could audit the source code until you are blue in the face, and you would never, ever find it.
That is deeply unsettling.
It is. And a defense against this wasn't conceptualized until years later by David A. Wheeler, using a technique called diverse double compilation.
Which is what, exactly?
Essentially, you take the suspect compiler's source code, and you compile it using a completely different, independent, historically trusted compiler.
Okay.
Then you compile it again with the suspect compiler. If the two resulting binaries don't match bit for bit, you know the suspect compiler is injecting invisible code.
That's brilliant.
It is. But what's really amazing is that Thompson's annotated source code for his original historical backdoor was only actually published online in 2023.
Well, really, just recently.
Yeah. And I have to ask, what stands out to you about a creator standing up at an award ceremony and proving that his own masterwork cannot be fully trusted?
Honestly, It takes a staggering level of intellectual honesty.
It really does.
He isn't selling a product, you know? He's dedicated to the raw truth of the logic, even when that truth exposes a fatal flaw in the entire industry.
Absolutely.
Which I think is a perfect segue to the man himself today.
Yeah.
Because he has received every accolade imaginable. The I.E. Hamming Medal, the Japan Prize, and the National Medal of Technology from President Bill Clinton for co-inventing Unix and C.
He essentially stimulated the growth of an entire global industry.
Yet, despite being a genuine titan of the information age, he is remarkably pragmatic. He's married, has a son, and there's this detail from the source material that just makes me smile every time I think about it.
The laptop thing.
Yes. It notes that he was an Apple user for a while, but he eventually switched his operating system to Raspberry Pi OS.
I love that so much.
Because of restrictions and issues he faced with Apple products.
It is the ultimate full circle moment for him.
The father of modern computing, the guy who mapped out perfect chess endings and designed the standard for the modern internet, got so fed up with his lockdown consumer laptop that he switched to a hobbyist operating system that runs on a $30 circuit board.
Because at his core, he is exactly who he was in the 1960s.
Exactly.
The man who built Unix from a discarded PDP-7 machine just to play space travel still prefers an open, accessible system that he can control and tinker with. He rejects bloat. He rejects closed-off layers. He just wants to touch the logic.
So what does this all mean? As we bring this deep dive to a close, think about your own workflow today. Every single time you open a browser tab and the characters render perfectly across the globe because of UTF-8. Every time a backend server queries a database instantly using regular expressions.
Yep.
Every time you touch an operating system, macOS, Linux, Android, that traces its lineage directly back to Unix in the C language, you are living, working, and communicating inside Ken Thompson's digital world. He poured the invisible concrete.
And that invisible concrete runs much deeper than most of us want to admit. Which really leads to a final thought I want to leave you with, based on his Turing Award speech.
Okay.
If our entire digital infrastructure is built on compilers that build other compilers, a massive, unbroken chain of translation stretching all the way back to the mainframes of the 1970s, how deep could a fundamental flaw be hidden right now before anyone noticed?
It's a scary thought.
Thompson proved definitively that clean, perfectly audited source code does not guarantee a clean system. So, does the sheer staggering complexity of modern software mean we are simply forced to place blind trust in the ghosts of code written decades ago?
It certainly makes you look at your smartphone a little differently, doesn't it? The physical structures around us, the skyscrapers and the suspension bridges, those are easy to trust because we can verify the steel. But the invisible metropolis we rely on for absolutely everything is built entirely on logic, on layers of automated translation, and on the enduring legacy of a few intensely curious minds. Keep questioning the invisible systems around you. Thank you for joining us on this deep dive.